this video, we're going to be veering toward the abstract and talking about inner product spaces. The concept here is we're going to be generalizing the notion of a dot product. The dot product is one type of inner product, but if you're in a vector space that's something other than Rn, or even Rn with a different type of product defined, the inner product is going to replace the dot product. It's going to satisfy all the same properties, but it might be defined in a vastly different way. So let's remember some things about the dot product in Rn. This is the Euclidean inner product. If you have a vector v and it's v1, v2, and you have a vector u, and that's u1, u2, our dot product is defined by taking v1, u1 plus v2, u2, and then you add these together and you just get a number. That's how we usually define dot product. And while we're at it, let's go ahead and review some of the most important properties of the dot product. So v dot u, as we've just defined it, is the same thing as taking u dot v. It just doesn't matter if you've reordered u and v in this equation. Also, if you have three vectors, u, v, and w, then u dot v plus w is the same thing as u dot v added to u dot w. It distributes over vector addition in that way. If you have a scalar involved, then a scalar multiplied times u dot v, which is a number, is the same number that you'd get as taking the scalar multiple of u dotted with v, or u dotted with the scalar multiple of v. And lastly, if you take a vector and you dot product it with itself, you're definitely going to get a number which is greater than or equal to 0. And it's equal to 0 if and only if v is actually equal to the 0 vector. So these are four very important properties of the dot product. So what if we're dealing with a different type of vector space? The space of matrices, the vector space of continuous functions, or something else. Is there something like the dot product? Well, what if we were dealing with functions, and we took the function f of x as our vector to be e to the x? This is a continuous function, and in the vector space of continuous functions, this would be a vector. How would we dot product this with g of x equal to sine of x? We can't use dot product the way that it's defined for vectors in R2. That just doesn't make sense. And if we try to multiply them together and take e to the x times sine x, well, this doesn't give us a number. This gives us another function. So we've got to do something different when we deal with a different vector space. Is there something that is similar to the inner product? And the answer is yes, there is. The inner product in general is going to be a function that satisfies all the same properties that the dot product does. That's basically the definition. Said a little bit more formally, if we have a vector space, we take two vectors, u and v, and we let c be a scalar. An inner product on that vector space is a function that associates a scalar to the pair u and v. For us, that scalar is usually a real number. And it needs to satisfy four properties. It needs to be true that if you take the inner product of u and v, it's the same thing as taking the inner product of v and u. We're using the notation bracket u and v for our general inner product. This is going to be the function that works like dot product, even if it isn't actually dot product. So an example of this is going to be what's over here, the usual dot product. So you can think of that when you're trying to put these rules into context. The second axiom that needs to hold is that u paired with v plus w gives you the same thing as adding together u paired with v and u paired with w. That's this rule over here. Scalar multiplication works in the way that it works for dot product, in the sense that you can scalar multiply times the scalar you get from u paired with v, or you can move that scalar into either the u component or the v component. And if you pair v with itself, it needs to be positive, and it's 0 if and only if the vector is the 0 vector in that vector space. So we can define an inner product. Essentially, it's going to be something that behaves just like dot product, even if it's defined in a drastically different way. And as for a little bit of terminology, what we're going to say is that an inner product space is a vector space that has an inner product defined on it. So what we should do next is look at lots of examples of inner products defined in a familiar place like R2 that are different from the usual ones. We need to look at things that fail to be inner products, and we should look at some examples of inner products using continuous functions. For our first example, let's look at three things. All of these are going to be for vectors in R2. So our vectors we're going to still be able to describe as u equal to u1, u2, where u1 and u2 are real numbers. You can think of it as being x and y in the xy plane if you like. So the first inner product is just the dot product. Now, we already know that this is an inner product. It satisfies the 4 axioms that we need. This is what we saw on the previous page when we reminded ourselves of 1, 2, 3, and 4 for the usual dot product. These are things that we saw in the very first lectures of this class. So that's definitely an inner product. But what if we change up the definition of the dot product just a little bit? Instead of taking u1v1 plus u2v2, we're going to throw in a 2 and take u1v1 plus 2 u2v2. If we redefine dot product with this new formula, this is also going to be an inner product. But if we use -1 instead of 2 and we use subtraction instead of addition, it's no longer an inner product. So let's check 2 and 3. And what we're going to need to do is for 2, which is an inner product, we need to verify that all 4 of those axioms hold. And then when we go around to number 3, what we're going to do is find some axiom that breaks, and that'll be enough to say that it's not an inner product. So let's go through the process of verifying all 4 of those axioms for the inner product on R2 when it's defined in this funny way. This is a formal process by which we check 4 formal rules. The first of these is that uv needs to be equal to vu. The way we've defined it, uv, the inner product of u and v, is u1v1 plus 2 times u2v2. Now, if you flip the order of the v's and u's in this expression, you get v1u1 plus 2 v2u2. And the way that adding and multiplying numbers works, it's the same number. So we have equals. And this is what it means to take v with u. So this rule was really easy to check. How about the second rule? Now we want to see that u paired with v plus w gives us the same thing as u paired with v and u paired with w. Again, we follow the rule. We want to use the definition of this new inner product. And when we do this, it helps to think of v plus w coming from the second entry here as being inside parentheses. So that when we write this out and we take the first components of u and the first components of v, we have u1 times v1 plus w1 in parentheses, and 2 u2 times v2 plus w2 inside parentheses, because we start from the inside out when we evaluate this expression. Then use simple arithmetic to write it out, and regrouping terms, we see that this is u paired with v and u paired with w. Checking the third axiom is also similar. We're going to take the scalar multiple times the pairing of u and v. So c is on the outside of a big set of parentheses. And then simplify the expression and recombine terms to see that it's cu and v. Finally, what does it look like when you have this new inner product of v with itself? Just following the rule shows you that you get v1 squared plus 2v2 squared, which is certainly going to be greater than or equal to 0. And equal to 0 if and only if v1 is equal to v2 is equal to 0. So what we have done here is we've checked 4 rules, the 4 axioms that, from the previous page of our notes, made up the definition of an inner product. All 4 of those rules hold, so that means that this new thing that we defined is an inner product on R2. So as it turns out, there's not just one way to do an inner product on R2. The dot product that we so commonly use is just one special inner product. Let's finish up this overall example by seeing why if we were to use u1v1 minus u2v2, that modifying it in this way produces something that fails to be an inner product. The issue is going to be with axiom number 4. So let's write that out a little bit more carefully. To see that if you define the inner product in this way, it's not actually an inner product, what we're going to observe is that it is not necessarily the case that pairing a vector with itself gives 0 if and only if v is equal to 0. This is a crucial axiom and it's going to break down. So take, for example, any vector v where v1 is not equal to 0. When you pair that vector with itself, v1, so this is a special vector where the first and second entries are the same thing, then what you get just by following this formula is v1 squared minus v1 squared, and that's equal to 0. But v1 was not equal to 0, and this shouldn't happen. This means that this axiom fails. And that means that when you try to define a product this way, it's not actually an inner product. Next, what I'd like to do is go over 2 examples of how to define an inner product for vector spaces that are something other than Rn. And the first one that we're going to look at is a vector space of continuous functions. How do we define an inner product when our vectors are functions? This was the issue that we raised before when we had e to the x and sine x. How do you multiply these things together? So let f and g be any two continuous functions on the closed interval a to b. The way that you define the inner product is by taking an integral. You do the definite integral from a to b, and there you multiply them together. Our problem before, when we had, say, e and sine, was that if we multiplied e to the x and sine of the x, we didn't get a number, we got a function. But the way you turn it into a number is to evaluate it at b and a, or to take the definite integral that goes from a to b. This is how you define an inner product on the vector space of continuous functions. Now, I'm not going to go through the axiomatic check of the 4 rules. What that amounts to is a kind of routine exercise in single variable calculus. It's the kind of thing that you would do in a good calculus class or an introductory real analysis class, so I'm going to skip that here and refer you to your textbook if you'd like to see that worked out. I just want to mention that this is how you can define an inner product if you're dealing with the vector space of continuous functions. Next, let's look at a different example. How might we define an inner product if we're dealing with vector spaces where the vectors are made up of matrices? Well, let's look at the 2 by 2 case. There's an inner product defined on the vector space M22. This is the vector space of 2 by 2 matrices. If we take 2 of them, let's say A and B, then we can define an inner product like this. We'll take the inner product of A and B to be equal to A1, 1, B1, 1. So take the first 2 entries and multiply them together to give you this term. Then take the next 2 entries multiplied together to give you this term, and then the next 2 entries and the next 2 entries and add them up. This is actually a lot like a dot product, and you can kind of reparameterize things to just interpret it as a dot product. But at least in this way, you can define an inner product on the vector space of matrices as well. The last thing that we're going to do in this video is to mention 4 really important concepts that you get out of an inner product. These are things that we have seen before when we dealt with the dot product. We talked about these in the first 2 lectures of class. Notions of the length of a vector, the distance between 2 vectors, the angle between 2 vectors, and the concept of orthogonality. So these things have a very natural interpretation when you're dealing with the standard dot product on Rn, Euclidean distance, and how you measure the length of things. Well, as long as you have an inner product on your inner product space, you can make a similar definition. So if you have 2 vectors in your inner product space V, then let's define the length, also known as the norm or the magnitude of a vector. We use the same notation, a double absolute value type symbol. This is going to be the square root of the inner product of U and U. Think about what we do in its normal dot product. When we're just dealing with the normal dot product and we're dealing with the length of a vector, U, in say R2, then the length of that vector U is the square root of U1 squared plus U2 squared. But this quantity that's inside the square root, this is just the dot product of U with itself. This is the square root of U dot U. The inner product is now generalizing the dot product. Dot product is an inner product, so when we define the inner product this way, another way to write this exact same expression is the inner product of U and U. So what we're doing over here is saying if you have any inner product whatsoever, you can make an analogous definition of the length of a vector. Now, it may not look like the length of a vector as you would normally think of in Euclidean space. If you're dealing with continuous functions and if you're doing the integral from a to b, it's going to look something like this. If you have f as a continuous function, continuous on the closed interval a to b, then what that length is going to look like is going to be the square root of the integral from a to b of f of x dx. And that looks a lot different than how we normally think of distance in terms of Euclidean space. But abstractly, what we're doing is we're putting the inner product of a vector with itself inside the square root symbol. And so that's how we're going to define the length of a vector. In a similar way, we can also define the distance between 2 vectors. That's going to be the length of u minus v. Whenever you have vectors, you can subtract them. and then you get a new vector, and that's what would go inside this inner product that goes inside the square root symbol. The angle between two vectors is going to be found from the inner product of u and v divided by the lengths of u and the lengths of v. That's cosine of theta, where theta is the angle between these vectors. And we can also say that u and v are orthogonal when their inner product is equal to 0. In the video that follows this, we're going to be working through some computational examples where we calculate things like length and distance and angle in vector spaces that we don't normally deal with.